just a broad overview of the entire book. So it's a lot, that's why I said bring snacks. All right. Your goals here, the whole complex knowledge of AEMT, the airway, respiratory, circulatory, which makes sense, because if you don't understand how the body works and what all's there, then you're not going to understand any of the rest of it, right? All right, normal cell, AEMT, fluid balance in the body, association with electrolytes. I'm not going to require you to know all the electrolytes. I couldn't tell you all the electrolytes and the percentages, but we are going to kind of hit on them a little bit as we go through it. And we are going to talk a lot about acid-base balance, because that's super important. A lot of your test, your your AEMT registry test is based off of physiology, okay? They have a ton of it on there. I've heard from quite a few students that the AEMT was actually harder than their paramedic test, which I kind of believe based on some of what I've seen. So just fair warning, okay? You've got to understand how homeostasis works and what it means. Somebody tell me what it is. What is it?
It is a balance in the body controlled by positive and negative feedback mechanisms.
All right, so in regular old English,
The body in its normal state.
body in its normal state. He gave a very good textbook definition. All right, but basically what it boils down to is keeping it equal, keeping it level. If we get too jacked up, we're going to bring it back down. If we get too low, we're going to bring it back up, whatever it takes. Everything has to work together to accomplish that, okay? Let's see. Metabolism. What is metabolism? Chemical reactions in the body that typically are going to fuel the rest of our chemical reactions in the body, all right? A couple of different types of metabolism. It depends on kind of what you're referencing, what types of metabolism there are, okay? We're going to hit that a little bit more. Understanding the level of organization. What's the smallest unit in the body? Your atoms, right? What do they make up? Molecules. Eventually builds up to a cell. We'll go ahead and skip forward a little bit. Cells make up, not quite, tissues. Cells make tissues. Tissues make organs. Organs make organ systems, and they make us. All right? You're going to be able to repeat that in your sleep by the end of the semester. That's important because that's exactly how shock progresses, but it starts from the smallest level and works its way up to the full level. So shock starts small, localized, can still be fixed, and works its way up until we die. All right, so that's how we die, little bits to big bits. All right, so I firmly believe if you want to know how things work, you got to know what all's there, and if you want to know what the abnormal is, you got to know the normal. If you don't know that normal, if I told you their blood pressure was 190 over 110, I see some looks like, ooh, that's not good. That's good. You know what normal is. What is the normal blood pressure? 120 over 80. All right. Can it be 116 over 70? Absolutely. Can it be 130 over 90? Absolutely. But there's a range of normal. If you don't know what those normals are, then the abnormal is just going to straight over your head. You'll never know. All right. What is anatomy in and of itself? Like, what is the definition?
The makeup of the body. The structure.
All right, structures of the body. What's the physiology?
How it works.
How it works. Anybody in here not have anatomy?
I'm taking it.
Are taking it now? All right, excellent. It does help. And y'all, terminology is huge, important too. It's like a cheat book, okay? If you know terminology, you may not have a clue what is happening in that question, but you can pick it apart and at least figure out most of it based on the words that are there. So if you're not strong in terminology, come see me. I got some books I can loan you. You can go through them, look at them. It really is like a little cheat sheet. Talked about the different levels of organization, the cell, cytoplasm, and organelles. What do those things do? Make up the cells. Okay, what does the cytoplasm do?
Protects the cell.
Kind of protects the cell. That's more the cell membrane. The cytoplasm kind of gives it the structure, right? That's the jelly kind of like stuff that's hanging out in there for all the other stuff to reside in. All right? All right. Chemicals, we know that. Chemical environment. Chemistry. Anybody ever taken chemistry? Oh, it sucks. It's hard. I did not like it at all. Okay? We're not going to go super depth into chemistry, but you do need to know that it exists and kind of what it deals with, okay? So it's composition of substances and interactions and how these things interact together. Chemistry happens. Y'all ever do the volcanoes in school, like elementary school, where you do the baking soda and the vinegar and whoosh, here it goes? That's a chemical reaction, okay? That kind of stuff, not quite to that degree, but that kind of stuff's happening every day, every breath that you take inside your body. All right? I'm not going to ask you to know all of those, but you need to know that it's happening. Chemical element, substance that cannot be broken down any further. And I know this is super exciting stuff, but bear with me. We got to get through this to move on. All right, an atom, simplest unit of an element. Your subatomic particles, electrons, negatives, protons, positives, neutrons, neutral. Neutron sounds like neutral, right? Protons, positive. It's a P. So that way, and then electrons are the leftovers. So they're the negatives. All right, you need to know what the difference there is. Your charges are what allow different things to kind of swap places, all right? These positives and negatives. Remember, your body's always trying to get that state of equilibrium, that balance. So positives and negatives are going to constantly be swapping back and forth in all different cells all over the body, trying to keep that equilibrium there. All right? Ion, cation, anion, electrolyte. What's an ion?
It's the, it's negative, yeah. It's the.
That's a cation.
Oh,
A positive ion is a cation. And an anion is a negatively charged ion. It's a charged particle, okay? So it's kind of both, really, negative or positive. But cation has a T, which looks like a plus symbol. That's your positive. Anion, and in medical terminology, what does an A or an N mean?
Not without.
Without. So if you see that, you know it's without something. In this case, it's without a charge. And then electrolyte. It's a salt that can't be broken down any further. They're located in a good abundance in your body. Here's just a picture of your atoms. Okay, you kind of see your neutrons, your protons, your electrons. They're all circling around, doing their thing. All right, different elements in the body. I'm not going to ask you to know this. I just want you to be aware of the majority of the elements in the body. Hydrogen, oxygen, carbon, and nitrogen are your most common ones, okay? Hydrogen is super important. Why is hydrogen super important?
Part of what makes up water.
It's part of what makes up water.
It's one of the most common ones in the body.
It is. All right. Hydrogen is also what our body is measuring to see where we are on that acid-base balance, on that scale, that pH scale. Because pH is potential of hydrogen. All right, so that's where we're measuring where we're at. And that pH, everything has to be in that right little narrow area to be right. Oxygen, of course, we know why that's important, right? You know, you die without it. All right, water. Composed largely of water, your body, how much percentage did they say it is? 70, somewhere in there, 80, a lot, right? Now, all of this water is going to be concentrated in a couple of different areas. So, intracellular is going to be the water within your cells. Ooh, there's your nice little picture. They don't have a neck. Okay? So, you've got water in the cells. That's intracellular. Extracellular breaks down into two parts. You've got outside the cells, and then outside the vessels. That's a terrible drawing, but it is. It's a happy drawing. All right, so intravascular, break it down. Intra means inside, and vascular is dealing with the vessels. All right, so intravascular is within the blood vessels. This is going to be the water that's with your part of your plasma moving around there. Okay, when we give fluids, when we give somebody fluids, it becomes part of the intravascular fluid volume, assuming that you got your IV appropriately seated in there. All right. Interstitial, this is around the tissues. Okay, this is where, have y'all ever seen somebody with CHF where their feet are really, their lower legs are really swollen? Sometimes they even start sweating, like the fluid will start seeping across, and it's a really kind of oily feeling, but their legs are so tight, and you touch it, and like it stays dented in. All that fluid is interstitial fluid, and basically what's happening is their intravascular space is overloaded, so it starts seeping out, trying to equalize out, and it seeps into that interstitial area. And then eventually, there's only so much room, starts swelling, okay? And then, of course, intracellular, within that cell itself, this is just all over the body, okay? Solutes, Foreign particles in bodily fluids. Bunch of different things this could be, but solute in and of itself just means some formed element, okay? Most of the time when we're talking about solutes and osmolarity and all that kind of stuff, we're talking about salt, okay? Sodium. But it can be any of those things. We know osmosis is water of movement across a semipermeable membrane. What does that do? What's the point of that?
It's part of like the balancing.
Part of the balancing. The body has a couple of different ways that's going to move stuff. All right, the two most prominent being active transport, which requires energy, and a helper, usually a helper protein or something, and diffusion. All right, so the body has figured out that it's a lot easier to move water to balance things out than it is to move salts and all these other electrolytes or other proteins. All right, so it's a lot easier. So a lot of this is going to be based on water movement. All right, now osmotic pressure, and a lot of this initial part is just definitions. It's just definitions before we get into it. All right, your osmotic pressure. This is the difference in concentrations of solutes. And what they do, most of your cell membranes are going to be set up with a dual layer. And the osmotic pressure is kind of what keeps them together. Okay? And what keeps water or solutes in the right spot. If not, they'd just be moving around willy-nilly doing whatever they felt like. All right? That's measured in milliosmoles. The natural osmolarity in the body is like 280 to 310. Your range of osmolarity in the body. The only reason you need to know that is because of your solutions. Your IV fluids that you give are measured in osmolarity compared to the body. All right? So if it is isotonic, iso means what? Same. All right, so it's going to be within that range. Hypotonic, and tonic meaning tonicity, the tonicity of this. Hypotonic means it's going to be lower, and hyper is going to be higher than that. You don't have to know anything else about milliosmoles. Just know that it is used in relation to fluids when you're putting fluids in the body, whether they're hyper or hypo, and those are going to cause things to happen in the body. All right, but that alcoholic pressure is what's going to keep all of your cells basically correct. All right, and then there we just got a little bit of head, but your isotonics the same, hypertonic, and then hypotonic. All right, any questions? We good so far? Some of y'all look like you're hating this already and regretting your decisions to be here. Huh?
Slow down a little bit.
Yeah. Can you back up?
Keep going, just gear down a little bit.
All right. Tell me, yeah, I got a little bit of Yankee in me, and sometimes I just, I get excited about stuff and I start talking. Throw a flag. Feelings will not be hurt. All right, so your isotonic. What's that thing?
Red blood cell.
Red blood cell. All right. So solutes, all these little tiny particles, right? And it's kind of suspended in your solution. You remember that way back when? Like 9th grade, maybe science, 7th grade? I don't know. So everything is moving back and forth, and these solutes are transferring, and then the fluid is transferring. Remember, it's easier to move the fluid than it is to move the solutes, okay? So your isotonics are not going to cause a net movement of fluid. The fluid, if it's intravascular, is going to stay intravascular. If it's intracellular, it's going to stay intracellular. It's not going to cause fluid to come out of the cell, and it's not going to cause fluid to go into the cell. Everything is going to stay right where it's supposed to be, okay? Now, your hypotonic has less cells, less solute in the cell than the surrounding tissue, okay? So relatively, that means it's going to be a little more concentrated within the cell. It's going to pull water in the cell to try to dilute it down, try to equal it out, try to make everything homeostatic on outside of the cell and inside of the cell. All right, so a hypotonic solution is going to pull water into the cell. All right, do y'all have a hypotonic solution? You do. All right. D5W. D5W. Dextrose 5% in water, basically is what that means. All right, that is your hypotonic solution that you have. This is great. Can you think of something like a time when you'd want to give fluids that will make the fluid that you put in their veins go into their cells?
Hypoglycemia.
Hypoglycemia, absolutely, because we got to have sugar to get in the cells, right? All right, what else? Hypertonic means that the concentration in the surrounding fluid is a lot greater than inside the cell. All right, so once again, it's going to try to equalize out. So a hypertonic is going to pull extra water, or just water in general, from the cell. Okay? Once again, certain circumstances, that might be a good thing. But here's the problem. If you put too much hypotonic solution in there, water is going to keep, fluid's going to keep going in the cell, keep going in the cell. It's like a balloon. Eventually, what's going to happen to it? It's going to pop. And then that cell's no more. Okay? Hypertonic. It's going to pull water out, pull water out. Eventually, it's going to shrivel up like a little raisin and do what they call, it's lice. All right? Not like head itchy lice, but lice. That just means to die, to do away with. Okay? So either one of these in extremes are bad. Make sense? All right? Registry loves this crap. And it's extraordinarily complicated, and it's just one of them things that it'll take you like 5 times of hearing it to wrap your head around, and that's okay. All right? So if right now you think I'm just absolutely insane and have no idea what I'm talking about, that's okay. We'll keep hitting on it, I promise. All right? Sodium potassium pump. You got your proteins on your cell membranes. That's a better drawing that I was trying to do up here. All right, so you got your cell membranes. All right, and then remember we talked about active transport, passive transport. We'll briefly hit on that. So when you're doing your active transport, you're going to have a way to get in and out. You got to have a doorway, right? You didn't just appear in the room. You came through a doorway. So that's kind of what these proteins are. They keep everything proper. What's supposed to be on the outside, it keeps on the outside. What's supposed to be on the inside, it keeps on the inside. Okay, and then it's the passageway for things to exchange as needed. All right, the sodium potassium pump requires energy. Okay, I'm trying to think of the best way to put this. So, y'all ever heard the term water follows salt?
Mm-hmm.
Okay, so there's lots more sodium inside the cell than outside the cell. All right, so with that case, if we were not constantly swapping the sodium out, what would happen with the water? Water would always be flowing in the cells. What would happen to those cells? They would burst, and then we would not be we wouldn't exist very long, right? Okay, so the sodium potassium pump requires energy. That's why we have to have the ATP, to constantly be fueling your sodium potassium pump as well as your other energy production in your body. Okay, that's what gives us our contractions in our heart, along with some calcium. Okay, that's the basis of everything else in the body working. If that shuts down and doesn't work, we shut down and don't work. Okay?
So ATP is just the substance that helps produce energy, or is it?
ATP is the byproduct. That's the byproduct of metabolism that we use as our energy cell, as our fuel cell, kind of, so to speak. All right? There's just another picture of it. Yay! Why do you think it's sodium and potassium? Why are they swapping back and forth?
They're both positive.
They're both positives. One comes in, if one comes in, the other's got to go out. They can't both coexist. All right. Energy requires, body requires energy here. Production, okay, is that chemical process of breaking down glucose. What are the 2 elements that are absolutely required for life to exist?
Oxygen and glucose.
Oxygen and glucose. All right. Without that, we die very rapidly. Now, how we get those 2 things varies. Okay, you've got backup methods, you've got primary methods, but either way, however it is that we're getting it, your bodies need a constant supply of both to fuel metabolism. So glucose, what's our primary method of getting glucose? Food, the food that we eat, right? All right, where's our secondary? If we don't have enough stores, let's say I'm keeping you in here and I won't let you have a snack because I'm mean, and your stomach's growling, you're feeling all weak and lightheaded.
Kind of like a backup in the liver or something?
You have a backup system in place, and it stores primarily in the liver. Anybody know what that one's called? What the storage is called?
Glycogen.
It's glycogen. Okay? Glycogenesis, absolutely. The fun little word. They all sound exactly the same. And they all mean almost the same thing, but not quite. All right, so glucose from the digestive tract back up from their stores. Okay? Oxygen, respiratory tract, right? What's the backup for oxygen stores?
I forgot the name of it, but there's something in the cells that store small amounts of oxygen.
Not enough to keep us alive though, not for real. We go to anaerobic metabolism. We don't move past it because the metabolism, aerobic means with oxygen, right? And anaerobic, if I can spell it, means without oxygen. Okay? A lot of people kind of picture this is the one that happens and then we back up to this one when oxygen's not there, but it's actually backwards. This is always happening. Always happening. Aerobic is what happens when we have oxygen in place. Okay? So our backup for this is that we just don't go to step 2. We stay with step 1. What's the downfall of anaerobic metabolism? Anybody remember?
Lactic acid.
Lactic acid buildup, and it's not very effective. All right? How many ATP molecules do we get from this?
2.
We get 2 ATP. How many do we get from aerobic?
36.
36. So this one, 2, this one, 36. Obviously, that one's going to be better because you're going to get more energy from it, right? Makes sense? All right, now, as far as metabolism itself, 2 major types here. You've got anabolism and catabolism. Anabolism is where you take something and you add it to something else, and together they make something. Y'all ever heard of anabolic steroids? Like the bodybuilders will take it and they'll build their muscles up and get bigger. Anabolic metabolism is building up of stuff. I'm really big on analogies. They may or may not always make sense to you, but they make sense to me, so I'm going to share them with you. All right, catabolism. Kind of to me sounds like cannibalism. All right, and cannibalism is breaking down of things. Catabolism is breaking down of things. So your catabolism is breaking down your glucose, all right, and producing your ATP. So we do have some anabolic metabolism happening in the body, but the main one that we're focusing on and concerned with is the catabolism, okay? Because without that one, we don't have energy. Without the energy, salt stays in the cells, water comes in, and we die. So it's simple as that, right? That's like all of AMP right there, summed up. 2 words, maybe 2 paragraphs. All right, ATP, adenosine triphosphate. Your first phase, that one I was talking about, the anaerobic, first phase, goes through a process of glycolysis. Recognize that. Glyco meaning sugar, and lysis meaning the breakdown. All right, so it's literally breaking down the sugar that you're ingesting, and it nets you 2 ATP. I think it ends up like it nets you 4 ATP, but it costs 2 ATP. So you end up with a net of 2 ATP there. All right, your glucose, first stage, broken down into pyruvic acid. All right, that is your anaerobic metabolism. What's the problem with pyruvic acid?
It's acidic. It makes the
It's
body.
acidic, so pyruvic acid is going to make your pH drop, which gets more acid, more acidic. All right, we're going to learn that the body does not function well outside of its range of happy on the pH scale. Okay, anybody know what the pH scale is? You don't answer. 7.35. 7.35 to 7.45, right? All right, so that's our happy spot. If we are outside of that happy spot, bad things happen, okay? So with pyruvic acid, it is an acid. It's going to create a lower pH, which is more acidic, right? What else is the problem with pyruvic acid? It's not very effective. Our bodies aren't effective at getting rid of it. We can, but it's hellacious on your kidneys, and it's really rough. Y'all ever had like a really good workout and your muscles just ache afterwards if you don't stretch appropriately before and after? And sometimes even if you do, they still ache and it feels like somebody just frogged the mess out of you and your muscles. All right, that's lactic acid. It's a close cousin. All right, that's because our bodies aren't very efficient at getting rid of these acids. Okay, it takes a little bit more effort and energy. All right, now, so that's where we stop. If we don't have oxygen present in sufficient amounts, we stop right here. So we've got 2 ATP and pyruvic acid that's going to mess up our pH that we can't get rid of very easily. All right, so we can do it for a little while, but after a while, our body's going to be like, I'm out. Okay, now, if oxygen's present, we move to the second one, which is aerobic. All right, that's going to start the Krebs cycle. The Krebs cycle is going to go through your catabolic metabolism, and it's going to break down pyruvic acid. It breaks it down into CO2 and H2O. What's CO2?
Carbon dioxide.
Carbon dioxide. How do we get rid of carbon dioxide? Can we get rid of carbon dioxide?
Very easily.
How? Exhalation. We do that pretty routine-like, right? So that's a very easy way for us to get rid of the byproduct. The other one, H2O, water. How can we get rid of excess H2O? Sweat. Do what? I couldn't hear you. Water pills, which is going to make what happen? Kidneys, all right? It's going to make you pee it out extra, all right? You were talking earlier about you drink all of your water and you'll be peeing all day long. That's why. You got extra water in there. What else? Tears, sweat, just through your skin in general. You breathe out a little bit with your exhalations. You ever like breathe in a mirror and you see the moisture droplets on there? Y'all didn't watch a lot of like mystery shows as a kid, did you? I did. They'd always put like, they weren't sure somebody's dead, they'd put a mirror under their mouth and to see if they're breathing or not. So, a bunch of different ways to get rid of that. So, this one, which also nets you 36, which is like 18 times more, I think, than the other one. Much, much more efficient. You get a whole lot more energy, and you get byproducts that you can deal with. And it takes the bad byproduct of pyruvic acid that you can't deal with and turns it into things that you can easily deal with, CO2 and H2O. With me? That's another picture. Okay, this is kind of your different types of metabolism, just with maybe better drawings than I have. All right, your pH was said on it earlier, but potential of hydrogen. All right, so if it is an acid, that means it is a substance that can donate a hydrogen, and if it's an alkali, it can accept a hydrogen. Everything is on a pH scale. Okay, oh, wait, hang on. Put my 0 in the wrong spot. All right, 0, 7, and 14 are kind of your hallmarks here. 7 is considered to be neutral. All right, so this is our neutral. Anything less than 7 is considered to be an acid. Anything greater than 7 is considered to be an alkali. All right? Now, this is relative to where you are on the scale, and there's different things as far as I think. There we go. So like water is neutral 7, baking soda is like an 8, 9, soaps around a 10, drain cleaners 14, blood's just a little above 7, tomatoes are about 4. It's all relative, okay? And when I say that, 7's neutral, right? And we said that the body likes 7.35 to 7.45, okay? So that's our neutral. Even though we're technically on the alkalotic side, that's our neutral, our happy spot. So if that pH starts dropping and it gets to 7.25, is it alkalotic or is it acidotic?
Acidotic.
Even though it's still on the alkalotic side, compared to our normal, it is acidotic because it's closer to 0. Does that make sense? All right. And ditto, same, if you go up 7.55, then that would be alkalotic. Okay, that would be more alkalotic because it's above our normal range. And for some reason, that kind of throws some people off. So I just like to point that out. Even though it's still above neutral, it is considered acidotic for us. Now, as far as membrane potential, this is just your difference in concentration inside and outside. And it's saying it's basically got energy coiled up, like think like a spring almost. A spring is coiled up. What happens if you coil up a spring and let it go? Or compress a spring and then what's going to happen when you let go? It's going to expand, it's going to move, it's going to create more energy, right? Same kind of concept here with your membrane potential. It's energy, literally, that's potential. It hasn't done anything yet, but it's ready to when it needs to. Okay? Polarized just means what? It's got a charge, right? It's got an overall charge. You may have positives and negatives within the cell or the cell membrane, but overall, you've got an overall negative charge or an overall positive charge, okay? And then depolarization is where it discharges and releases all of that energy. This is what's happening in your heart right now as we speak. Every time your heart beats, they're polarizing, the cells are polarizing, and then they're depolarizing and sending that electrical current throughout the heart, which makes all the other cells squeeze and discharge, which makes your muscles contract, pumps the blood through your heart. Okay? All right, moving on. Cell membrane, that's your semi-permeable membrane, allows things to move back and forth, right? Your channels, that's what lets things go through that cell membrane. All right, cytoplasm, so the fluid inside the cell gives it its shape kind of. Your nucleus has your DNA, that's what decides what that cell is and does. All right, your RNA, what does that do? More things. You don't really got to know, I'm just letting you know it's there. All right, ribosomes do things. Golgi apparatus do things. Mitochondria do things. Mitochondria do important things because that's where what happens? It's producing ATP. The what? It is the powerhouse that makes your energy, right? All right. Vacuoles, centrioles, lysosomes, they're things that are in the cells. All right, there's a picture of the things within the cells. All right. I try my best. If you notice, like some things I kind of skim through and other things I drone on and on and on about it. I try to focus on things that typically are either more important in real life, like treating patient things, or very important, like test type things. I don't try to harp on things that are not super important in the grand scheme of things. Okay? So if you ever notice that, that's why. If you want to talk more about something I skim, let me know. We'll discuss. After class. I think that was a threat. Y'all better be nice. She'll get you. Tissues, all right, they are specialized. We know our cells make up our tissues, and our tissues make up our organs, and they make up other organ systems. What are the four main types of tissues? Whether, some specialize, some don't, but what are the four main types? Epithelial, connective, the other two, absolutely right. All right, so epithelial, connective, muscle, and nervous. Well, smooth is a form of muscle, all right? So epithelial, these are the linings of your body's surfaces, okay? Peritoneum, different things like that. You ever do dissections in high school or anatomy at some point? You know how like when you opened them up on the inside, there was like that really smooth layer? Or if you cook ribs, you got that smooth connective tissue on the back side of the ribs, unless they've scraped it all off. You need a better butcher? No? Yes? Anyways? Okay. So anyways, linings, the very thin linings of the bodily surfaces. In the lungs, you've got one cut set, the pleura, that lines the lungs, and you've got another set that lines the thoracic cavity, and there's like that thin serous fluid between them that lets it slide and move. Yes? I'm just that point being that they do different things in the body. Connective tissue, collagen and elastin, what's the point of that?
Hold things together.
Stretch and hold things together, give you form and function, right? This is what some people pay big dollars to dermatologists to inject back into them as they age. Filler. All right. Muscle tissue. What kind of muscle tissue do we have? Smooth, cardiac, and skeletal. Okay, so where's the most of your smooth muscle located?
In the intestines. GI tract.
GI tract, but organs, All right, so skeletal, that's like your actual movement, allows to keep you upright, move, slap somebody if they need it, whatever. And your other one, the cardiac, your heart, or lack thereof for some folks, Hard crowd. Nervous tissue, all right? This is our nerve cells, right? They conduct impulses from the brain and from the body and let the two connect and talk. All right, and you've got two major types there. You've got myelinated and demyelinated, and they do slightly different things there. All right, anatomic position. The proper anatomic position is important because when relating to other parts of the body or describing positions, narrative, it's got to be relative to this. This is the assumed position, okay? Palms are forward, otherwise standing like this, okay? Now, with this position are where we get our planes. The sagittal plane, it divides you into left and right. Most of the time it's assumed to be mid-sagittal, which is going to be midline in the body. But that's a vertical plane that cuts you in left and right sides. All right? Your frontal plane, measure the glass down this way to front and back sides. All right? And then your transverse cuts you, of course, in half. Where? Just depends on where you want to imagine it at. Okay? Doesn't really matter in the grand scheme of things. Mid-axillary. Show me the mid-axillary line on yourself. Mid-axillary. Alright? It's going to run, this is your axillary, armpit. Okay, and it's going to run, mid-axillary is going to run straight all the way down, with this being your median, your middle, basically. Do what?
Number 6.
Number 6. Alright, mid-clavicular. Alright, right here. Mid-clavicle. Okay? Your abdomen, they divide it up in 9 regions, but they also divide it in quadrants. I feel that the quadrants are easier. So, you know, that's what we're going to reference in here, because I don't remember. I mean, I know what 1, 2, I know where the quadrants are, but the names they give them, I'm like, so we're going to work on quadrants there. Now, your cavities. You got your dorsal cavity, your ventral cavity. Your dorsal is your brain and your spine. Your ventral is all the other. It's all of this stuff right here. Okay, and they just kind of sit there together. We know that organs or tissues, they work together. Let's talk about organs real quick. What's the one up here?
Brain.
What's the one that helps you breathe? What's the one that moves blood? What's the one that what's the one that regulates blood sugar? Pancreas. What's the one that breaks down and metabolizes most of our vitamins, minerals, and such? Liver. What generates or releases bile when eating fatty substances? Gallbladder. Where's that bile created? In your liver. All right. Where's the reservoir for a little bit extra blood, like about 350 mLs? About 350.
The spleen.
It is the spleen. All right. What is your filtration and elimination? Kidneys. What's your digestion?
Lower
And
intestine.
lower intestines. All right. Reproductive. I knew there was something else I was forgetting. Male reproductive. The testes. All right. All right. What about for female? The ovaries, and they also have the uterus. All right. Did I forget any? Did we cover them all? The skin. Ooh, good one. The skin, the largest organ in your body. Did y'all ever, like, I was a nerd, y'all. I still am a nerd. There is no was. I am. So one of my favorite things when I figured out what epidermis was, I always like to read. So I'd get words I didn't know what they meant, and I'd go look them up because, you know, nerd. And so when I figured out what epidermis was, and a lot of people, other people my age didn't, I'd be like, "Hat, your epidermis is showing." They'd be like, "What?" And I would laugh so much. I got so much enjoyment out of that. It was great fun for me. If you have somebody that's forgotten what it means, feel free to use it. You'll get a good laugh too. All right, so these organs do things, right? They work together to do things. Organ or system that provides structure to the body, we know that's bones, and we know the system that perfuses the body is your cardiovascular system. What makes up your cardiovascular system? Heart and blood vessels, and the blood, of course. Okay, here's your bones. Everybody stand up. I'm going to do a little stretch. We're going to touch your bones. Your bones, not your neighbors.
I don't have any bones. They don't work.
The older you get, the less they work. Enjoy it while you can. All right, everybody touch. What is this one?
Cranium.
What's just this particular one? Frontal. All right. Temporal.
Parietal.
Parietal. Some of y'all are not touching. All right. Occipital. All right.
C1 through 7.
C1 through 7, which are collectively the cervical. All right. What's different about C1 and 2 versus the rest?
They are.
They hold the weight of your head.
Axis and atlas, right? They hold the weight of your head, and they allow us to do all of this, which the rest of our spine doesn't do. So kind of important. All right, what's else different or important to note about the first couple of cervical vertebrae? They're thinner, smaller, and that's also where your branches of your phrenic nerve come out. Phrenic nerve is important because it innervates your diaphragm. Without the diaphragm, we don't breathe. You ever heard C3 through 5 to stay alive? All right, if you have a fracture, a high cervical fracture, the odds of losing your ability to spontaneously breathe go up tremendously. So there's that. All right, let's go. Let me make it a little easier. Pretend I'm poking behind my eyeballs in that area.
Zygomatic.
No, it's cheekbone.
Orbitals, all right? All right, a little bit lower here. What's this? All right.
No, at the point. No, that's your nose. That's your mandible.
Mandible. The one that's kind of up in here behind the cartilage? Vomer. Remember that one, Vomer?
That's the straight one.
That's the little
one
tiny
right
one.
behind it.
This is your mandible.
Yeah.
You said this is mandible.
No, maxilla. Did you say mandible?
Yeah.
Oh, my bad. I was just like, yeah, that's right. Keep rolling. See, I wasn't really listening. Oops. All right, so try again. Maxilla,
Mandible.
mandible.
Check something.
I was going to tell y'all a fun fact, and then I realized it had nothing to do with it whatsoever, so I was like, I should have not. Kanye West did a whole album with his jaw wired shut, which is pretty awesome. He couldn't talk, and he did it. I was like, oh, it's pretty good. Anyways, it's before he got a little crazy. All right, what else? Moving on down. Clavicles. These look pretty gnarly if they're ever dislocated and hurt. All right. Scapula.
Humerus. Radius. Oh,
Radius.
I can't name all of them.
Them things. I'm cool with just carpals.
The irregular ones.
Or short.
Can't remember the
Or
correct.
short.
All right.
Phalange. No, that is the.
Metacarpals.
Those-
Spirit fingers.
Phalanges.
Spirit fingers. All right. What else we got? These up in here.
C-spine.
No,
Not here. C-spine's up here. The bump, that's where C-spine stops.
I said T-spine, not C-spine.
Oh, T-spine. Let's not call it that because that sounds a lot like C-spine. This is your thoracic. How many do we have? 12. Breakfast at 7, lunch at 12, dinner at 5. All right, so 7, 12, 5. You ever need to know how many are there? There you go. All right, what's down here? Lumbar. What about right here? Part of your pelvis. They've got a couple of different bits and pieces. All right, you've got your ilium, which is kind of the big crest, and then you've got your ischium, right, which are kind of like the right little parts kind of towards the front, and then you've got your acetabulum. Those are the little loops at the bottom because you sit on your ass, right? All right, that's fine. All right, what about this? Femur. What about that? And the big one that you drill? The other one that you don't? All right, little fellas right here. Tarsals, y'all stop touching. You should be touching. There we go. All right, and then spirit toes. The toes. There we go. Excellent. All right, you can sit back down now if you want, or you can stand. I don't care. So, makes up our skeletal system. We've got our bones, our cartilage, our tendons, and our ligaments. They give us support and structure, protection. This is why our most important things are protected by the thoracic cage because they need a little extra love, a little extra in their life. All right, they are. Didn't see that. They also hold our extra calcium. Is where our bones store extra calcium, bone marrow, and that's where what happens? Red blood cell production, right? It's also highly vascular, which is why we can drill into most of them and give fluids and other medications because it has a main line into your vascular system. All right, you start off with more than 206 bones. I don't remember how many off the top of my head, but it's more, and then some of them fuse as you get older, and you end up with about 206. Some people, a little less, a little more. Fun fact, one we did not name was the one bone that's not connected in any shape, form, or fashion to any other bone. It is that little floating thing. Hyoid.
Yeah, that.
Hyoid.
At the end of
No, it's back there.
It's way back in there. It's kind of like a little horseshoe type shape back there, but it's not connected by cartilage, I think, to anything else. I think it's like just connective tissue that keeps it in place. So there's that. All right, cartilage, what does it do? What's the purpose? What is its goal in life?
Protection of the joints.
Protection of the joints. How many of y'all are missing some cartilage from high school sports or other things, all right? What happens when you don't have that cartilage? It hurts. Y'all ever heard the crunchy grindy sound? Sounds like you're standing on some Rice Krispies. All right, well, in these joints where you have the cartilage, they have synovial fluid, okay? It's in the bursa. And normal circumstances, when you've got a fully encapsulated bone end with your cartilage present, it's smooth and it rubs together nice. It glides. There's no friction, almost no friction, and there's pain-free. All right, but when that starts getting worn away or torn or otherwise damaged, now you've got bone ends which are not as smooth, and it starts grinding together and causing a lot more pain and a lot less effectiveness. All right, tendons, what do they do?
Muscle to bone.
Connect muscle to bone. Only way I ever could remember which one was which one, Achilles tendon. Because I know, I had this fear growing up that I would be like in a bathroom stall and somebody would cut the back of my heel and cut my Achilles tendon. Like, I won't be able to get away because they got me. I can't walk.
That movie where they.
Luckily, it never happened. But you know, I always knew that was like my calf muscle and my foot. So that's the way I can remember which one's which. All right, ligaments do bone to bone. Some of y'all may have also had some of those replaced at some point in time with some surgery. They have a tendency to get torn, especially your MCLs and your ACLs and your knees. A little bit of sideways motion, your knee just spazzes out. Does not like it a bit. All right, there's your bone. It's a thing. All right, so you've got your cartilage on the end of it there. Inside, you got your spongy tissue, your marrow. The outer lining is called the periosteum. Makes sense. Ost is dealing with bone. Peri means around, so periosteum. All right, the diaphysis. I can't ever say it right, so I'm just going to break it while I want to say it. The diaphysis is the shaft. It's the middle part. All right, the connection here is the metaphysis, and then the epiphysis. This is where your growth plates happen. Okay, so that's where you don't want to break it as a kid when you're still growing. It's bad. All right, inside you've got your arteries, your veins, your nerves, your bone marrow, your things. Good? Everybody good? Your short bones. Look at that. It's in here. I forgot. Short bones, wrist and ankle. All right, roughly cube shaped. All right, flat bones, your sternum, your ribs, your scapula, and your pelvis. What's interesting about, tell me something interesting about flat bones. Anybody have anything interesting? They're flat. Mm-hmm. If they break, they tend to break in more than one place, especially with the pelvis. All right, long bones, your extremities, right? Your B? Huh? Oh, Dean. Okay, I see what you're saying now. I was like, what are you talking about? Your long bones are your arms and your legs. All right. Axial skeleton, this is your skull, your spine, your ribs, and your sternum. So it's basically not your extremities. Okay, it's the center part. It's the core. It's what gives you your upright kind of position there. Your appendicular is the rest. It's your pelvic girdle, your arms, and your legs. All right. Why is it important to know the differences there? Just because the book says so. You ever heard the term axial loading? From trauma and EMT probably at some point. Axial loading is where you have excessive force being put on one end or the other of the axial skeleton. Much more likely to cause vertebrae fractures, skull injuries, that kind of thing. So it's not good. All right, but anyways, axial, center, appendicular, everything else with the pelvis. Muscle systems, we're good. Everybody feel good about that? Good little review there for your bones? All right. We've got a few more minutes, then we'll take another break. Muscle systems, all right, you got your cells, I've got your actin and myosin. What do those allow you to do? Allow them to move, right? They constrict or contract and they extend, so they allow for that movement. If not that, we'd be like blobs, essentially, on bone, not moving, not doing anything. That'd be a terrible life, all right? With your contraction stimulation, how does that make it happen? How's that electrical stimulation making that muscle contract? Are you wanting to answer? Or you got another question?
I'm wanting to answer.
Okay, go ahead.
If I remember this correctly, feel free to assist me on this one, Brittany.
She's calling you out.
We took the same class. I still have nightmares about this one. Action potential travels down the neurons, crosses the synaptic cleft.
What were you saying?
You want to know how muscle contraction occurs. This is how I
Can you speak in proper English, please?
He actually is, but
No, I can't understand what's coming out of
hold
your
on,
mouth.
I'm gonna translate. I got you.
Thank you.
Remember when I said don't overthink things? This is one of them times don't overthink things. So the nerve impulses go through and they create a difference in the potential energy. All right? So they discharge the potential energy in the cell and make it contract. When you do enough of those, the tissue will do the same thing. Y'all ever done the wave?
Yeah.
Like, woo, all right, let's do the wave. Y'all start it. We're going to go. Everybody's going to do it. Do the wave. Y'all, you gotta stand up for the wave.
Oh,
That's too much work.
I'll give you 1 bonus point on your quiz.
Alright then. Good.
You stand when the wave gets to you. Y'all have never done the wave. Y'all lied to me.
what's it?
Start the
I
wave.
don't get bonus points, right?
And back. We're going one more time. All right. Now, it's half a point each time. Now, the point of that, it started here, but it had a ripple effect all the way through, right? Same thing with your nervous stimulation of your muscles. All right, so it starts and it travels throughout the cells, throughout the muscle tissue, so it creates an effect on the entire muscle. That makes sense a little bit? All right. So, different types of muscles. We kind of hit on this a little bit. We're going to touch on it again. Your skeletal muscle or striated muscles. Those are what are attached to your bones and allow for your movement. Okay? Your smooth muscle, involuntary control. So, what's controlling your smooth muscle? Nervous system. What part of your nervous system?
The one that tell it to,
The one that tells it to do things? Autonomic nervous system, right?
yeah,
All right, because it's automatic. All right, it does it automatically. These are the things. If you had to think, stomach. I just saw somebody. Yeah. Okay. Cat's eating. She's eating some crackers. She brought snacks. All right. I'm calling you out. If she had to sit here and think, chew, 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 swallow. All right, peristalsis, do your thing. Chew, 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 all the way to stomach. And then she had to think, chime, do your thing. Break it down. Starts breaking it all down. Then she had, hey, liver, do your thing. All right, start absorbing when it gets to the small intestine. Oh, wait, port. I need you to open up. Valve, open up. We're going down. Right? We're in the lower intestines and we're in the small intestines. Liver, come absorb. All right, bloodstream, you pump. Right? Me too. All right, you wouldn't get much else done. So your body's like, I got you. It's cool. I'm going to do it for you. You just pay attention to Jessica rambling on and on and on. All right? So it does it for you without having to think about it. Cardiac muscle. It's also under involuntary control, but it's kind of cool because it's a loner and it does what it wants when it wants. It's got, the brain is like kind of keeping it in control, but the heart's like, if I want to go faster, I'm going to go faster and you can't stop me. All right? It's like that annoying little kid on the kindergarten playground. You can't do anything. Boo-boo. All right? So your cells have a unique property in the heart. Have y'all started on the heart ones yet? Have y'all looked at that, like the automaticity and all that stuff for your disease portfolios? Maybe. One day at a time.
Wait, when you do?
All right. So your cardiac cells, your cardiac cells have a couple of unique properties. One of which is automaticity, which means they're capable of generating their own electrical impulse.
Oh, the contractility and those things.
All that stuff. Yeah.
Conductivity.
All right. Now, moving on. Integumentary. All right. This is your skin, the largest organ that we almost forgot about. Good looking out. Made up of a couple different layers: your epidermis, your dermis, and your subcutaneous. And if you look at it once again, dermis. What does that mean? Skin. Epi. Top or outer. All right. And then just dermis. And then subcutaneous. Cutaneous being
Inner.
sub meaning below, and cutaneous is dealing also with like the fat and other kind of stuff layers. All right, you can see you've got hair follicles, you've got sensory receptors, sebaceous glands. What do the sebaceous glands do?
Produce oil.
Produce oil. Some folks, they have overachiever sebaceous glands, and some folks have underachievers. They've got like the Sahara Desert on their face. Whatever, they're there. All right, your erector pili muscles. That just sound fun. What do those do?
Basically give you goosebumps.
They're goosebumps. They give you goosebumps. When your hair stands on end, ching. All right. Why do we do that? Just throwing out some fun facts. You don't have to do this for a test. Temperature usually, or other things like an awareness, like autonomic type things, that something's just like, something ain't right. Hair stand up on end. But it's to insulate us if we're cold. And just like that early awareness level. You ever seen some, like spiders and stuff, their hairs will stand up as like extra sensory type organs? That's essentially another way that our body uses it as that kind of extra little way there. Anyways, so that's the stuff. There it is. It is the largest one. It maintains our body warmth and protects us from external pathogens. If we didn't have it, every little bug that we came in contact would be all up in us, literally. All right, this is why it's important to protect your skin. If you are prone to dry, cracked skin, get some really good lotion, seriously, because you're going to wash your hands a lot in EMS. You should anyways. And if you're not, you're going to be using alcohol-based hand sanitizers, which also dry out your skin. Cornhuskers lotion is amazing lotion, really, really good for keeping your skin not cracking and peeling, which, you know, you'll do it if you work in the field. You'll start noticing you'll get calluses and your knuckles will start drying out and cracking, and it's terrible. Keep them healthy. It helps keep you healthy. All right. We talked about the layers. If you have substantial damage to your skin, a large abrasion, disease, or something burns, what's that going to do to your overall body chemistry, your overall body homeostasis? It's going to throw it off. All right, because we know that it protects us from pathogens. So number one defense, they have taken out our castle walls. All right, our castle walls are down. Is it going to be a lot easier to invade the castle?
Yeah.
Absolutely. All right, body warmth. We have to maintain a normal temperature in order for homeostasis. For everything else, all these pieces have to be there together working, or else they won't work at all. So if we lose a big chunk of our skin's ability to do that, then you lose regulatory function as well. You also lose the ability to maintain your sweat, which helps maintain your fluid balance. All right, so all these things kind of play into it. All right, respiratory system. We get oxygen in, get rid of the byproducts, right? Excess water, excess carbon dioxide. Now, it's very important to note respiration versus ventilation, okay? You have to know the difference here. In EMT, usually it's more of a, are they breathing, right? But you're not usually evaluating really deep into it. So now we're going to be evaluating really deep into it. Respiration is the actual exchange of gas, okay? That's carbon dioxide and oxygen swap sides, like a hostage exchange, okay? Ventilation is just air movement. It's a mechanical process. You can have ventilation without respiration, okay? So ventilation, air comes in, air goes out. Respiration, gas exchange happens. When we get through with respiratory system, we'll take a quick break. All right, now, the ventilation process, all right, two phases. You've got active and passive, and we kind of hit on that quiz a little bit. Your inspiration is an active process. We know that the medulla oblongata stimulates, all right, it's got little measuring centers, chemoreceptors out in the body. The primary two locations are in the aorta and in the brainstem, all right, and they're measuring hydrogen. They're measuring the acid of the body. So when the acid levels get a little bit too low and it's getting a little acidotic, the body says we need to breathe to get rid of some of it, okay? It converts into carbonic acid and then disassociates really rapidly. Not super important, but just know it's measuring the acid levels, okay? And when they get off, it says we need to breathe. So it sends the signal, beep, 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 beep. That's what I envision, that the noise it makes in there. All right, and it sends out the signal, goes down, exit the spinal cord through the phrenic nerve. Actually, is that a cranial nerve? Phrenic nerve. That's not a cranial nerve, is it? It's not. Okay, so comes down, exits through between the branches, leave out between C3, 4, and 5. All right, and you've got left and right side branches, but they come down and then it innervates the diaphragm. The diaphragm, when it gets its impulse, its electrical impulse, it contracts because that's what muscles do. And when it contracts, it pulls down here, which creates a negative pressure in the lungs. Okay, negative pressure in the thorax. Air comes in to equalize it out. Air comes in, hopefully makes it down to the alveoli. Gas exchange happens, and then the diaphragm relaxes, and the excess air comes back out to equalize back out to atmospheric pressure. All right? Kind of makes sense? We'll do it again. Don't worry, not right now, but we will do it again. All right? Now, as far as your gases go, partial pressure, this is how much an individual gas contributes to the total pressure. You don't really need to know this, but in aspect of measuring like the partial pressure, like as far as oxygen and carbon dioxide and stuff like that in the body, you may see it as lab values. Like PaO2 would be the percentage of oxygen in the bloodstream, okay? You see PaCO2, that's the partial pressure of carbon dioxide in the bloodstream. So they are important in that aspect, but you're not going to be measuring it, okay? But you need to recognize if you see a low PaO2, what's happening? they're hypoxic because they don't have enough. Does that make sense? All right. As far your ambient air, 79% nitrogen, like roughly 21% oxygen, other stuff. It is what it is. I hadn't changed from EMT here. We know that gases are going to follow diffusion, which means higher concentration to lower concentration. So that's how this gas exchange happens. Pretend this is a lung. That's a lung. Whee, that's a little off-sided. Try that again.
It only has 2 words. It's okay.
There we go. We'll just leave it a little lopsided. All right, so air comes in. You've got your, what's this? Trachea. Where does it branch? What's that called? Carana. The actual place where it branches off is called the carana. All right, and then you've got right here is the bronchi. And then they branch off into bronchioles, and then they end in the alveoli. Okay, so alveoli look kind of like grape clusters covered in capillary beds. All right, capillary beds are special because they're one cell thick, right? So it's very easy for things to move back and forth across them. So right now in these capillary beds, you've got lots of oxygen. No, wait, no, you don't. You got lots of CO2. See how easy it is to convert? All right, why do we have lots of CO2?
Waste byproduct.
Waste byproducts coming back to the alveoli for gas exchange. Air coming in has lots more. Uh-oh, I made it too. That was big. Let's put a few of them out here. All right, so it has lots more oxygen than the capillary beds surrounding it. So diffusion's gonna happen. All right, so carbon dioxide is going to seep across into the alveoli, and this oxygen's gonna seep out into the capillary membranes. Gas exchange has happened. Diffusion has happened. It's trying to equalize. And then once that process happens, diaphragm's relaxing. Anything that's still in here is going to start making its way out. All right? O2 is bound to hemoglobin. What is hemoglobin? It's that thing that's right there in the back of your brain.
Yeah, it's not gonna.
It's a protein.
Yeah.
It's a protein. All right, it requires iron to be bound. All right, that's why if you give blood, they check your iron levels. They will make sure you got enough to keep for yourself before you go giving the rest away. All right, so it uses iron, bounds to the, where is it found? Red blood cells, all right? And then oxygen binds to it, and it's toted around through the body. Picture, if you will, with the cardiovascular system, it's a train track, okay? All of your vessels are train tracks, or a road if you prefer roads. I like trains. And then all of your hemoglobin that are bound to the red blood cells are train cars. And they're choo-choo. The heart is the station, and it gets on board, and it's choo-choo-choo-choo-choo-choo all the way through the body going wherever it needs to go. And they're constantly, passengers getting on and off doing their gas exchange, okay? The O2 is bound to the hemoglobin. Carbon dioxide is carried in 3 different ways. It's formed in bicarbonate. That's one of those chemical reaction thingies. All right, it's bound to the hemoglobin, or it's dissolved in plasma. The ones that we're primarily looking at, your body's measuring, are the ones that are usually bound in plasma, okay, or the free, all right? Now, oxygen, we know, is used at the cell, all right? How does it get to where it needs to go? The vessels, okay? How does it know when it's time to hop off and go out into the tissues? Goes back to the pH. So as long as the pH is within that normal range, the cells basically are going, I'm next, I need some, whenever they need some oxygen. And it'll hop off the hemoglobin train when it gets to it. If that pH gets out of whack, they tend not to stay bound for the appropriate lengths of time, so they either go way too far and miss their destination, or they hop off early and don't get to their destination to begin with, all right? But oxygen, anyways, I'm getting a little ahead of myself, sorry. Let's see where we at. Oxygen fused for alveoli, we've already done that. Oxyhemoglobin dissociation curve. Going back to that pH. It's a whole big long word that basically means, all right? This is oxygen bound. Okay? So if the pH drops too low, oxygen disassociates early. Okay? So it's the vagrant jumping off the train. If you're going to Atlanta, you hopped off in Noonan. Okay? You didn't make it. side, isn't it? Okay. If your pH goes up, all right, you stay bound too long. You meant to go to Atlanta, but you went to Savannah instead, which may not be a bad trade-off. But your business was in Atlanta, all right? When your pH is just right where it needs to be, you go to Atlanta and you get off in Atlanta and you handle your business. And then you get back on and come home. All right, so decreased pH, it jumps off too early. It doesn't stay bound long enough. Increased pH, it stays bound too long and it misses its stop. So if the knee's hollering out for some oxygen, it keeps on going and that knee still doesn't have its oxygenation it needs. All right. Boyle's law, this is just the pressure of the gas is inverse with its volume. I'm not going to ask you about that because it's not going to directly play in with what you need to do day to day. All right, there's your upper and your airway. What is our cutoff for the upper and lower airway? What's the differentiation? Where does it stop and change over? Huh? You're like my kid when he thinks he's being funny and he mutters something under his breath, and I'm like, "What'd you say?" He's like,
No, at the larynx.
larynx, at the larynx. So everything above the larynx is upper airway. Everything below is lower airway. Makes sense, right? Upper airway, air comes. Dadgummit. Upper airway comes in. Where does it come in? The oropharynx and the nasopharynx, right? In the nasopharynx, you've got these little turbinates, those little rough ridges that kind of move the air around and warm it up and humidify it, and all the little hairs that are in there, they pick out the bad particles. That's what makes your boogers. So your boogers are actually your body helping you. They're like saying, "Hey, I got your back." All right? So they're picking out the bad things, the particulates, warming up that air, sending it on down. All right? Then it travels down. Then you got your actual pharynx up in here. Then it keeps on going down, hits your vocal cords and your larynx, right? Then we go into the lower airways. It hits the carina, bifurcates. You got your bronchi and your bronchioles, and then your alveoli. Pretty simple, right? Y'all got this. That's what I already said. That's also what I already said. The respiratory membrane, this is where the gas exchange happens. This is where the capillary beds and the respiratory membrane on the outside of the alveoli meet. Okay?
So I think there was a question about, it was on the outline for the portfolio. What were you looking for, like, I think he said something like the process of gas exchange.
Air coming in and like O2 coming in, carbon dioxide coming out the capillary membranes, and gas exchange happening there.
But it's okay.
You get what you put out of it. I mean, you get out of it what you put in it. All right. Now, backing up a bit, you also, when we talked about respiration, right, you got ventilation and respiration. You also, for respiration, have internal respiration and external respiration. Where does the internal respiration happen? Inside. In the body. All right? It's happened at the cellular level throughout the body. External respiration is happening at the outside, and so that's in the lungs because it's a gas exchange with the outside world. All right? So if you see that, and you will, external, outside world. Internal, inside the body gas exchange, because that whole process that happens in the alveoli also happens at the cellular level throughout your entire body. At the cell level in every tissue. Okay? Your lungs have lobes. Your right side has 3. Your left side has 2. Why is that?
Because of the heart.
Because of the heart. All right. You got your visceral pleura. Now, you'll see pleura a lot. There's lots of pleura in your body. There's pleura. So, with your visceral, if you see visceral pleura, I know it's terrible, but it's good. The visceral pleura covers your viscera, which are going to be your organs. Okay? You ever heard the term visceral reaction? It means like a gut reaction, like you just instantaneously hate somebody for some reason. It's a gut reaction. All right, viscera, visceral. That means the organs. Parietal is the outside, the lining of the cavities themselves. Okay? And then, like, your pleural fluid, that's just your lubrication to let everything glide so you don't get the friction rub in there. Your hilum, point of entry from the bronchus, the bronchi. Okay? Your pulmonary vessels carry your blood from the heart and back and forth. Which one brings blood to the lungs? Deoxygenated blood to the lungs.
The arteries.
Pulmonary arteries, all right? And which one takes it back to the heart? Pulmonary veins. They're swapped, right? The only ones in the body that are swapped, unless you were pregnant and then in utero, the vessels are swapped as a baby. All right? As far as oxygen carrying capabilities is what I mean by swapped. All right, your bronchial vessels, oxygenated blood from the aorta back to the lung, we're back to the vena cava. That's what actually gives the lung tissue itself the blood supply that it needs. Like your coronary arteries supply the heart with its blood supply, that's what supplies your lungs with their blood supply. And respiratory cycle typically occurs every 3 to 5 seconds, 12 to 20 breaths per minute on demand. If we get up and we run around the building a couple of times, that rate's going to go up substantially because our metabolic needs have increased substantially, right? All right, so it just depends on what they need. If you're asleep, typically your respiratory rate's going to slow down because you're sleeping. You don't need quite the same metabolic demand. All right, the primary stimulus to breathe is that hypercarbic drive. That's where I was telling you about the chemoreceptors. Where were those located? Remember? The aorta and the brainstem. Okay, so we're measuring the blood with the aorta and we're measuring CSF with the brainstem. And that's what's measuring that hydrogen, all right? So that's measuring where we're at with our pH, okay? If we get too hypercarbic or increased levels of your hydrogen there, then or CO2, then it's gonna tell you to breathe. Your backup method, because bodies like backup, they like to have a main method and a backup. Y'all ever heard of the hypoxic drive? Anybody ever tell you, don't give somebody with COPD lots of oxygen, you'll knock out their hypoxic drive? If they stop breathing, do you know what to do about it? Breathe for them, okay? Don't withhold oxygen from anybody that needs it. It also can take a good long while for that to happen. Anyways, your hypoxic drive. Basically what happens in cases of cigarette smoking or like being exposed to lots of factory gases or something like that over long periods of time, your body gets used to continuously high levels of carbon dioxide. For instance, do you have a smoke alarm in your house? Okay. Have you ever had a little period of time where it went off on everything? Like you could just be steam from the macaroni and cheese you're cooking. We'll set that sucker off. You don't pay it any attention, right? You start turning it off or you take the batteries out and you ignore it. That's kind of what your body's doing with the hypoxic drive. You got a flag that's saying high carbon levels, problem, and it says hush yourself. You don't know what you're talking about. And so then it goes and starts measuring oxygen levels instead. All right, so when it's measuring oxygen levels, it's measuring when they drop. So let's say you're pattering along, 95%, all right, and all of a sudden they drop because you haven't breathed. Then the brain says, oh, warning, and then it'll kick in with a stimulus to breathe. All right, so instead of working on high levels of carbon dioxide to get those out, it waits for the oxygen levels to drop to tell you to bring more in. Kind of makes sense? A little bit? Okay. That's why they say if you give them high flow oxygen, their brain won't have that stimulus to breathe because the oxygen is going to stay consistently high. It takes a while for that to happen.
You said it waits for oxygen level to drop?
It waits from the hypoxic drive, it's waiting for the oxygen level to drop, and then that kicks off the stimulus to breathe instead. All right. Tidal volume. How much air is typically breathed in 1 minute? 500 milliliters, right? What's our dead volume? What's left in the bronchi, right? In the bronchioles, what doesn't make it to gas exchange. Minute volumes, how much is exchanged with each tidal volume? Over a minute, so tidal volume times rate. Vital capacity is maximum inspiration and exhalation. Residual volume is however much remains in the lungs. That keeps your positive pressure there because you're not going to breathe all of it out all at once. All right, that's what I already said about the medulla. Okay, chemoreceptors measure that pH. That's the chemical reaction that actually happens. Your H2O and your CO2 form carbonic acid, and then when oxygen hits it, it immediately turns and disassociates into free hydrogen and bicarbonate. You don't really need to know that. I'm just letting you know it's there. All right, that's if you're the really big why question, that's why. Got to get through this, and this is important stuff, and like all the pH and the balance and all that. And if you don't understand that, we're gonna have a hell of a time later on. So we got to get through this, and then we'll get to the rest of it. All right. Now, cardiovascular system, you got three main components. You've got the heart, you've got the vessels, and you've got the contents, right? Now, I like to use a pump. Some folks are car people, some people are firefighters, some people don't do any of that. That's cool. But you've got three main components, and I'm going to relate it kind of to all of them. Okay? So your heart is the pump. Anybody know what happens to a car engine when you don't put enough oil in it? It's going to stop working, right? All right, so if we're looking at cars, your heart's kind of the engine. Your vessels are all your tubes and your belts and all that stuff that are keeping it working, and your blood's going to be your oil. Okay, it's the content. If we want to go firefighting way, the heart is the pump. Truck, pump, pumper, okay. Vessels are going to be your hose. I like the firefighting way because it works really well with your 1.5-inch hose, 3-inch hose, and 5-inch hose. All right, but your vessel is going to be your container. All right, and then your blood's going to be the content. You can have a perfectly working pumper truck and amazing brand new hose, and if you got no water, it does you no good. Right? All right. I'm going to throw this out there just because I mentioned it. With your vessels, what happens if you've got a set amount of fluid, all right, set amount of water, and you push it, and you can use garden hoses if you garden or whatever. You have a smaller diameter hose. What's going to happen to the water coming out the end of it? With the same amount of pressure, the pump's working. It's going to be higher pressure, right? What happens if you take that same amount of water and put it through a 5-inch hose? It's going to be slower. That pressure is not going to be the same, okay? That's how our vessels are constantly adjusting. Our vessels, they got different layers, we're about to talk about that, but they're constantly adjusting in size to keep the pressure regulated throughout the body to keep the blood moving everywhere that it needs to go throughout the body. We measure that efficiency with blood pressure. All right, so it's actually pressure. Who knew? Heart's the pump, vessels are the container, blood is the content. When we have shock, it's a problem with something in here somewhere. Okay? Closed system, which means whatever's in there should stay in there for the most part, right? If we're losing it, it's losing somewhere, and that's a problem. That's not supposed to happen. All right? All right? Oxygenated blood. Let's trace blood through the body. Let's start in the right atrium. Okay, right atrium, where does it go? Right ventricle. And I know y'all are like, this is so stupid. I promise you there's someone in here who doesn't know it and is too afraid to say it.
Me?
So we're going to do it. It happens every single semester. Usually people won't tell me. We're going to do it. You're going to know by the end of the day. Right atrium. All right, that's where blood comes back from the body. Goes from there, drops down through your tricuspid valve into the right ventricle. All right, then it leaves the right ventricle, goes to the lungs. The whole oxygenation thing happens. Then it comes back to the heart. It's a little short circuit. All right, goes back to the heart and comes in through the left atrium. And then it dumps down through the bicuspid valve or mitral valve into the left ventricle. All right, and then it shoots out through the aorta. Woo, little aorta arch, like a little slide. All right, and then it goes down throughout the aorta, thoracic aorta, abdominal aorta, and so on, and branches off into all of your smaller arteries throughout the entire body. When it gets down into the tissue level, it's my version of capillary bed. All right, so coming into your capillary beds at your tissue level, fingers if you want, all right, they turn into arterioles, which just means smaller artery. All right, and it comes into your capillary beds, 1 cell thick. The whole diffusion thing happens again. That internal respiration happens here all over the body. Then, once it's done its thing, it keeps on trucking. It enters on the other side in the venules, which are small veins. And then those come back and meet and meet and meet and turn into your larger veins, which then eventually all dump into either the inferior or the superior vena cava. And then those just hop off back into the right atrium and repeat over and over and over again until you die. All right, let's do it one more time. Y'all say it this time, not me. We're going to start off right atrium. Where do we go from there? All right. And if you're having trouble, I'm going to draw this kind of heart because I can't draw the other kind of heart. If you're having trouble with your valves, try before you buy. Tricuspid before the bicuspid. All right, so right atrium, tricuspid valve, right ventricle, lungs,
Left atrium.
back to the left atrium, bicuspid valve, left ventricle, aorta, to the body. All right, and then the arteries eventually turn into arterioles, which then go into your
Capillaries.
diffusion-y stuff happens, chemistry. All right, then it goes back into your venules, your veins, superior and inferior vena cava. Hot damn, you know it.
You gonna put that on him?
We can. Yes, sir.
I'd appreciate
I'm
it.
sorry, this is kind of a random question. How big is the aorta, like, in comparison to something else?
Usually about the size of your thumb, maybe a little bigger. Garden hose, maybe. But on average, your heart's about the size of your fist, and your aorta is about the size. Your main aorta is about the size of your thumb, diameter-wise. Maybe just a little bit bigger, but it's pretty big. Like, you get a hole in it, you die pretty quickly. Now, the heart's really cool because let's just pretend that kind of looks like a heart. I'm gonna put some squiggles, some coronary arteries. And you got your aorta that comes up, the aortic arch. You got to have enough pressure coming out from the ventricles to make this arch and then go out into the body. All right. Your heart gets its blood supply because underneath this valve there's little holes. Okay. And so the blood comes up. Well, not all the blood. Some of it's a little bit underachieving. It doesn't make it over the aortic arch. Those valves close back down, and the blood drains down the arch that didn't make it out and empties into those little holes at the base of the aorta. And those feed the coronary arteries. So literally, it's the best thing ever. Every time the heart pumps and gives the body blood, it feeds itself. All right? But it's pretty smart. All right? It's a passive process, kind of, so to speak. It's pretty cool. I think it's neat. Nerd. All right, so oxygenated blood obviously has oxygen-bound hemoglobin. Deoxygenated blood doesn't. It has carbon dioxide or nothing or other byproducts of metabolism. Blood tissue, all right, it is tissue. We've got plasma and formed elements. What are the main components of blood? All right, so you got plasma, which is kind of like the river it's all floating in. Red blood cells, which do what? Oxygen and stuff. And then white blood cells, which do the army, right? They fight off your invaders, your infection and stuff. What's the other thing?
Platelets.
Like, you were super excited about that platelet.
No, I wasn't gonna answer. I didn't know this.
What do we do? What do the platelets do? Clots. So clots, absolutely, very good, very good.
Aren't there platelets in the plasma?
Yes, they're mixed all in with it. They're all mixed in with it. And you don't have as many, typically you don't have as many red blood cells floating around like in your normal healthy day. You've got some that are kind of your sentries out there checking out things, making sure everything's okay. But if you have an infection of some sort and your body recognizes invader, intruder alert, then it kicks production up into high gear, your white blood cell counts go up, and then they go start attacking. Like, it's like kind of like the reserve. All right, so you've got some army already doing their thing for the military. All right, but if something were to happen, they could activate National Guard, Army Reserves, and stuff, and have a whole lot more military readily available. Does that kind of make sense?
What makes white blood cells?
Why gotta ask a silly question like that? Because on the top of my head, I can't think of it. You got like mast cells, basophils. There's another one in there.
There's another one, but
There's another one, but I don't remember what it is. We'll be on test.
Miss Duncan,
Mm-hmm.
the only reason I can remember the 5 white blood cells is the phrase "never let monkeys eat bananas."
Well, that's just mean because they like bananas.
Well, that is neutrophils, lymphocytes, monocytes, eosinophils, and basophils are your 5 white blood cells.
You were doing better than I am.
Don't ask me what they do. I've already
I
forgotten,
won't.
thankfully.
I promise I won't.
I appreciate you.
They're made, white blood cells are made in the body.
But they are made in bone marrow like the red blood cells. Now we know.
see, I was gonna say, I can't remember. It was, I don't know.
You have to use some magic. It's called
Google,
Google.
right? It's amazing. 5 years ago, we'd had to open a book and search and get paper cuts looking. Maybe more than 5 years ago. Oh, that's
It's
been a
lot
while.
longer because I'm too lazy to look through a book.
All right. Average liters in an adult, 5 liters. Average in a baby, a newborn baby, about the size of a Coke can, 12 ounces ish. All right. Average in a ped, about 2 liters, 2-liter Coke. All right. Now this varies. You know, bigger people tend to have more blood because they got more tissue, more vessels. Smaller people may have a little bit less. It just all depends. Okay, but you know, your normal is going to be your normal. What keeps your body happy? Plasma, it's all this other stuff floats around in. Also, chemical messengers. Where are those coming from? Like, what part of the body system are those dealing with? Endocrine a lot of the time. So endocrine messengers essentially will be transported sometimes as well to go to other body parts to do things. All right, we already talked about hemoglobin and the protein there. Y'all want to talk about that more? Y'all feel pretty good about that? Bound by iron? Okay. Mature red blood cells, no nucleus. All right, that's where hemoglobin hangs out and chills. All right, looks like a nice soft little bed. All right. Lifespan, approximately 120 days, so we have to continuously be making them, all right? Now, some things will affect that. Sickle cell, for instance, has a shorter lifespan, so they don't last as long, so that's why they tend to stay anemic. Anemic just means not enough red blood cells, okay? There are other things that can affect it, but just know what your typical lifespan is. Now, when those reach the end of their life, what happens to them?
The spleen eats them.
Spleen eats them and shoots out what? More platelets. Some of it turns into platelet debris. All right, your hematocrit. This is volume of formed elements in the blood, mostly looking at red blood cells. Have you ever been in the hospital? You've heard them or talked about like H&H, hemoglobin and hematocrit? Basically, this is looking if you're anemic or not. Okay, how much oxygen do you have, or how much red blood cells do you have, how much hemoglobin, because if you don't have enough of that, you're not going to be able to carry enough oxygen. Make sense? All right. You're not going to be measuring that. It's just you need to be familiar with the term. Now, your different proteins that are apparent or that are present on the surface of your red blood cells, you'll recognize those as blood types. Okay, these are antigens, that little markers essentially on the blood. So you've got A, B, and O. Does everybody know what your blood or your blood type is? All right. Who's an A? Anybody an A? Do you know if you're A positive or A negative? A positive. What about B? B. What about AB? You think? And O. Somebody didn't raise your hand. Don't know? All right. If you ever go get blood, they'll tell you. It's kind of cool. But anyways, so I can give blood to most of y'all. If you are any of them positive, I can give you blood. I'm O positive. So what we're looking at, gotta erase my beautiful drawings. I'm sorry. Don't cry. All right. So red blood cells. Can y'all see that over there? So we're going to say this is O. This is type O. There are no antigens on the surface. All right? This is going to be type A. So we'll say that this has lots of little type A's attached to the surface. Those are your antigens. This is type B. You've got lots of B antigens. And then this is A and B. This is AB. So it's got both types of antigens on it. And what this is doing is looking at self or not self. So when you give blood, they type you. And when you're going to get blood, if you're ever injured or anemic for some reason, you receive blood, they type you because you want to get the type of blood that matches you. All right? So I'm O. If you give me type A blood, my red blood cells don't have any antigens on there. So you give me type A or B or AB, and my body's going to look at it and go, intruder. And it's going to attack it, and it's going to go try to kill it. It's going to cause a transfusion reaction, all right? If A tries to get B, same thing. It's not the same. It doesn't recognize it as self, and so it will attack it, all right? Now, AB, they're kind of lucky. They can get blood from anybody because they've got both markers. If I give blood as an O to somebody who has AB blood, my blood doesn't have that marker. So it doesn't, there's nothing there for it to recognize as not self. So it won't attack it. Now, it does break down one step further in the positive and the negative. Any of y'all know, I know you said you think you're positive. Anybody negative that you know of? Negative? All right. So y'all can only get blood from a negative person. Positive can get from either or. So it's looking at the RH factor. Okay, and it's named RH factor because of the rhesus. They discovered it when they were studying rhesus monkeys. Not Reese's Pieces, but RHES, something about like that. All right. So the rhesus monkey. So you either have it or you don't. And if you have that factor, that additional antigen, you're positive. And if you don't, then you're negative. So I am O positive. So I have the rhesus factor, but I don't have an A or a B marker. All right. What did you say you were? A positive. So she's got the A marker and the rhesus factor, and you were B? Negative. So he's got B, but he doesn't have the rhesus factor. So who can he get blood from? He's B negative. He can get blood from B negative. Is there anybody else he can get blood from?
O negative.
O negative, because we don't have any markers on O negative. O negative is a universal donor. AB positive is a universal recipient. It's also fairly rare. All right. Okay with that? We move on. Pretty good. A little bit. This does come into play, you know, like I said, giving blood, but also during pregnancy, because if maternal and fetal blood types are different, if they've been exposed, they may attack. So there's shots called ROGAM shot. I think it's a common thing they do a lot of times to take care of it. But anyway, there's that. There's your antigens, your RH factors. There's a little chart that tells you who you can give blood and who you can get blood from, just in case you're curious. All right, your white blood cells, these are your protection. These are your army, your military. These are, when something comes in that's not part of your body, it says intruder alert, let's go attack it. Now, as far as your actual immune system, you've got specialized attacks and you've got general attacks. Think Navy SEAL, okay? You've got specialized things that go directly in, and then you've got a general attack. Your general attack is going to be first, okay? That's your inflammatory response. That's going to be your fever, things like that are just generally designed to kill bacteria, viruses, fungus, whatever. All right? And then platelets. These are your small fragments that have been broken down from the breakdown of other fragments that aid in the coagulation cascade. All right? Here's your heart. Inside, those little, these little things right here are the tendinae, cordinae, something like that. I don't know. It's in the book somewhere. They're the strings. They're the heartstrings. And what they do is they pull, when the heart muscle contracts, they pull and open up the valves to allow blood to go through the chambers. That's all they do. They just look kind of cool, though. All right, your valves, your aorta, your vena cava, all your different stuff. You notice how this is a lot thicker muscle than over here? The left side is a lot thicker than the right. Why is that? Because it's pumping a lot further. The right side has to go here. The left side has to cover all of the body. All right. We talked briefly, we touched on the electrical system, right? So with this is kind of what we were talking about here. You've got what they call the pacemaker. Okay, the pacemaker is the SA node, that's the sinoatrial node. All right, and if you go into medic and you're doing like EKGs, sinus rhythm is the normal inherent rate. So electrical impulses generated in the SA node, and then you've got these little, they call them internodal pathways. Think kind of like the interstate. It's a faster way to travel. Okay, you can go back country roads all the way to Atlanta. Which way is going to be faster, that or hopping on 85? 85. So it depends on if there's traffic or construction. Most of the time, though, those pathways are going to be faster. So these are like your little superhighways here, and they're going to take this electrical impulse started by the SA node. And y'all, it's not some little like button in there. It's literally the cell that stands up and says, I'm the leader, follow me. All right, it's the leader cell, and it can be replaced, and then that leads to all kinds of other funky rhythms. So it follows through those pathways, and then it gets down here to the AB node. As it's traveling, it's causing a contraction of that heart muscle. So it's following through, and it's squeezing the top part of the heart. What's that going to do to the blood that's inside of it? It's going to force it down and dump it down into the ventricles. Okay? Now, the ventricles are a fair amount bigger than the atrium, right? So it's going to take longer. We want a full flush. We don't want a half pump. When I say that, flush the toilet. What happens if you flush the toilet immediately right after? Like you flush it, it goes down, and then you immediately try to flush it again. What's going to happen to that toilet bowl? It's nothing. Yeah, exactly. There's nothing to flush out, right? So nothing's going to happen. That's kind of like what we're doing here. We don't want to beat again too fast. If you wait a second, it gets it full, then you get a full flush again, right? So this electrical impulse is going to pause at the AV node, which is the atrioventricular node. It pauses here to let this finish filling up before it discharges again. Okay? So blood's filling up. Then once it passes through, I mean, when I say pause, we're like, and gone. It gets it's like a hiccup more or anything. All right? Then we're going to come out here. We've got the bundle of His. And then that bifurcates and goes into the left and right bundle branches. And those go, the left bundle branch goes to the left side of the heart, the right bundle branch goes to the right side of the heart, and travels down the septum and kind of loops back around at the bottom, coming up the sides of all sides, and innervates. And those are the Purkinje fibers. Now, it does this, the reason it rapidly comes down here and then comes back up. If you squeeze the toothpaste tube from the top, what happens? You run out of toothpaste really quick, right? So if you want a good squeeze, you squeeze from the bottom. So here, you squeeze from the bottom of the heart. So if you've ever seen a video of a heart beating, it's like it almost rocks. It's like squeezes and squeezes back up to meet it. Google it. It's fun. It's really cool. All right. Now, you've got something called inherent firing rates. Okay, all of these little nodes and things in the heart have a set predetermined happy spot. All right, so for your SA node, your inherent firing rate, I don't know if that's the right word, but I'm going to use it anyways, is 60 to 100. Does that sound familiar? What is that?
Pulse rate.
That's our normal resting pulse rate, right? That's normal because when it's working properly, that's where it's going to be, okay? Unless some needs have exceeded that, and then it'll speed up. Now, going down, your AV node. Your AV node's kind of like the second string, okay? They practice with the big boys, but they don't always get to play, so they may not be quite as talented as the first string at getting the job done, all right? They can do the job, just maybe not quite as good as the first string. This is your second string. Your AV node. It will take over. If the SA node says, deuces, I'm out, it'll take over. But it's not as good at it. It doesn't have the practice. So its inherent firing rate, it's not quite as good. 40 to 60. Okay? Then, the Hail Mary. When you beat the team by 1 point. All right? The Hail Mary at the end. When all of this has already gone out and failed, nothing else is happening, you've got your Purkinje fibers. Supposed to be like a J. All right? And they're really not good at it. This is the walk-on. They've never actually played. All right, these are the bench warmers. But they may keep you alive until something else can fix the problem. Until you can get the ice on that. I'm just going too far with that. I'm done with that. It's the backup. All right? 20 to 40 beats per minute is your average. How long will that sustain you?
Not very long.
Not very long, okay? Because remember, the whole oxygenation thing, we've got to have an adequate amount of blood moving through to bring us glucose, to bring us oxygen. So if this is not pumping enough, it doesn't matter how much is present if there's just not enough moving throughout the body, right? All right, so that's your backup. That's probably fairly good information to have there. Now, just throwing this out there for the people that like to know a little bit more, when these go wrong is when you start getting all your funky rhythms. If you go too fast, if you've got multiple pacemakers fighting for it, that's when you get your AFib. You get your VFib when all of this is firing off chaotically and it's all just like basically spazzing out. So all of your different rhythms all relate to something being wrong in one of these areas. Your AV blocks, it's holding it a little bit too long. All right, so different things, different ways. Go to EKG, go on paramedic, you'll learn more about that than you ever thought you would need to know. All right. Now, that's, guess marker's done for the day. That's exactly what I just said. All right. Regular cycle events, each beat, right? All right, we know that the electrical impulse goes through the muscle, it causes muscle contraction, and that pushes the blood throughout the heart and then throughout the body. Calcium is required for contraction of the myocardial cells and the myectin. not super concerned with that. That'll be more when you get to cardiology. But just be aware calcium is required, adequate amounts of calcium. Cardiac action potential. You've got systole and diastole. Do those sound familiar? Blood pressure, right? Okay, so remember back when you learned about blood pressure, systolic blood pressure is the force under pressure, right? The contraction. All right, diastole is relaxation. That's the residual pressure in the vessels, right? Right. You know you got 2 pumps in one for the heart. All right, now your pathophysiology here, your electrophysiology. A couple of different properties that make your cardiac cells special and unique. All right, automaticity. That means they can generate their own electrical impulse. Excitability. This allows them to very easily respond to electrical impulse and contract. All right, conductivity means they can rapidly move the electrical current through the cells and pass it on to the next one so that you can get that uniform contraction of muscle. And then contractility, they actually have the ability, if needed, to squeeze harder to get that extra pump in there in times of need. Now, of course, that can't happen continually all the time. Eventually, you're going to wear it out. Right?
So the 4 unique characteristics of retention on the exercise.
Yes. Now, cardiac output is just how much blood is ejected from the heart, period. All right? 2 things come into making up your cardiac output. You've got stroke volume and heart rate. Now, our heart rate's how many times it's pumping, obviously. Stroke volume is how much blood is coming out. All right? Think of this kind of as like an equation. If we want to maintain the same cardiac output, all right, and our heart rate is lower, how do we do that? We want this to stay the same. This goes down.
Increase stroke volume.
We've got to increase stroke volume, okay? If heart rate goes up, can stroke volume go down? All right, may not have to beat quite as hard, all right? But one of these 2 things is going to have to give. One of these 2 things is going to have to adjust to maintain cardiac output. And that's where the whole mechanisms of shock come in. What we recognize as shock is the body's signs and symptoms of maintaining cardiac output. All right? What the chemicals are doing to your body. So stroke volume, how much blood's getting pumped out every time. Average cardiac output is 4.9 liters per minute. So pretty much all of the blood in your body every minute. Pretty impressive, I think. With this, I'm not going to ask you to know numbers, okay? Don't think of it as numbers you got to fill in and solve for. Just think of it as if one of these adjusts, the other one's going to have to adjust to maintain, okay? All about keeping that balance. Now, preload is just the blood coming back to the heart, all right? So in order for the blood to go out, you got to have blood coming in, all right? That's preload. That's all that is. Preload, blood coming back to the heart. Contractility, the heart has to be able to adjust how hard it squeezes. So that's going to affect, which one's that going to affect? Heart rate or stroke volume? Stroke volume, all right. Squeeze a little bit more, you get that extra little bit out. Afterload is the pressure that the heart has to overcome to squeeze the blood out. So the residual pressure out here in the veins and the arteries, the heart has to overcome that, has to overcome that pressure to squeeze and push the heart or push the blood out into circulation. Does that make sense? Okay. If everybody got up right now and tried to squeeze through that door all at once, okay, how much harder are you going to have to work to make sure you make it through first? Work a little bit harder. All right? So if nobody's going through the door right now and you try to get out the door, how easy is it going to be? Pretty easy. All right? It's kind of like with the blood in the heart. You know, it's that residual pressure. You got to get through that pressure to get it out of the heart. All right? And if that made no sense to you, just ignore it. Keep rolling. All right? It's Frank Starling's law. Frank Starling's law is basically like a bodybuilder in the 80s. Did y'all ever see pictures of Arnold Schwarzenegger before he was governor? He's all like, you know what muscle bound means? Like the muscles get so big that like they can't put their arms by their sides because their traps are huge and they're like, and this is as far as they can put their arms down, muscle bound. The same thing can happen to the heart. Essentially, Frank Starling's law means that the heart, the more you use a muscle, the bigger it gets, right? Common sense. You exercise, you work out, your muscles get bigger up to a certain point. And up to that point, when it reaches that tipping point, which varies based on person, all right, now the heart gets bigger, 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 stronger, 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 and it hits that wall. And now it gets muscle bound and it gets ineffective. It gets too big and it gets kind of floppy and it stops pumping effectively. So now stroke volume is going to tank because we're not getting good squeezes because we're not effective. So our heart rate's usually going to have to pick up the difference. Does that make sense? Okay. I'm going to do afterload and preload. Are we good? This is important stuff. I know it's a whole lot to digest. We'll keep touching on little pieces as we go, I promise. Just don't dip out on me now. Stay with me. All right, now, with your vessels, arteries, veins, capillaries. Arteries have something, veins have something, capillaries don't. Capillaries are one cell thick for a reason. They need easy access. They need things to be able to pretty freely move between them. All right, arteries and veins have an inner layer here. All right, so you've got your tunica externa, tunica media, and tunica intima. Intima meaning intimate, close, inside, media, middle, external, right? Well, inside this tunica media, you've got muscle. You've got smooth muscle that are under automatic control. This smooth muscle is controlling what size hose you're using. Okay? So if for some reason our cardiac output has dropped a little bit, your body has little sensors all throughout it that recognize it and say, hey, we need to fix that. So it sends out its chemical messengers and it tells the blood vessels to get a little bit tighter, because if we make that diameter smaller, the lesser volume can still produce the same output. Does that make sense? All right. If we've got an overload of blood, we've got too much volume, all right, it's going to reroute some to the kidneys, but it will also make them relax a little bit, give it a little bit more room to try to lower that blood pressure, because we don't want that pressure too high, because then the heart has to work harder to get the blood out. And hearts get tired. We don't want the heart to get tired. Hearts get tired, we tend to start dying. Okay? Veins, of course, you got the valves. We talked about the valves, kind of like that lock and dam system, moving the blood throughout. All right? Vasculature is just another term for blood vessel. We already talked about arteries, capillaries, and veins. And we know the goal of cardiovascular system is perfusion, right? Perfusion just means circulation of the blood and its contents to meet the needs of the body. That's all perfusion is. All right. Arterial blood pressure is that force the blood exerts against the walls of the arteries. We measure that with our systolic and diastolic. We know the systolic is during contraction of the heart. Diastolic is residual. MAP, mean arterial pressure. This is important, but I'm not going to ask you to do much with it right now. But when you go to medic, if you go to medic, you'll be asked to do something. And essentially what's happening is, instead of, when you get to that level, you're not so much looking at a minimum blood pressure, you're looking at a minimum arterial pressure. And that goal is like 60 for cerebral perfusion. But mean arterial blood pressure, you take your diastolic blood pressure plus 1/3 of the pulse pressure. So let's say the blood pressure is that good old 120/80. All right, so diastolic blood pressure is 80. What's the pulse pressure? Anybody remember? Pulse pressure is just the difference between systolic and diastolic. So pulse pressure would be 40. All right, times 1/3. Uh-oh, that's 2, not 3. Somebody math that for me. All right, so 40 times, what'd you get? 13 point something. So 13 point something
I'll give you 93 point something.
plus 80 gives you 93 point something. All right, that's enough to have cerebral perfusion. Pretty good perfusion. All right, that's all that's looking at. It gives you a number, and you know you need at least this much perfusion to keep the brain working. If the brain stops working, the rest of us stop working. I'm not going to ask you to do this. I'm not going to ask you to do this math. I just want you to be aware of what it is. Okay? Moving on. Nervous system. All right. Brain, spinal cord, nerves, nerve cells, right? Your nerves are kind of cool. They have different little things, and they're designed for really fast transmission of electrical stimulus and information. So on this side, you got your cell body, your nucleus, and your dendrites, and they're like little tree limbs, okay, reaching out. And then you've got a long axon. This is helping bridge the gap between them. And then on the other end, you've got your little fingers, all right, and in between these are going to kind of line up like this. The gap between them is the synaptic gap, and that's where your neurotransmitters come into play because they kind of help you jump the bridge, so to speak. You just know what they are, okay? These, you have afferent and efferent, okay? Different types of nerve cell. All it means is it taking information away from the brain or is it taking information to the brain? You have automatic shortcuts. For instance, you ever burned yourself touching something hot on stove or campfire or something? What do?
Jerk back.
You jerk back and you just say a bad word, right? You start jerking back before you even realize it. And usually then that pain kicks in and starts hurting. All right, that's your body kind of looking out for you, because if we had to wait for hot, ow, that's hot, you should do, oh, move hand, all the way back, or we'd be burned, we wouldn't have fingertips anymore. All right, so it's little shortcuts. Any bad stimulus, it's going to automatically try to remove it from you, or you from it. All right. Neurons, basic unit of function. I already talked about neurotransmitters there. Somas, cell body, dendrites, fingers.
Typo.
Where?
Neurons and target.
Huh? Where? What?
On the neurotransmitters.
Oh, yeah.
Oh, I wrote
That
it
was a
for
stutter.
I wrote it for against.
That was a stutter. All right, now your nervous system is broken down into two different types, or several different types, but you've got your central nervous system and your peripheral, right? What does your central nervous system consist of? Brain and spinal cord. All right, so that's going to be usually like control and function type stuff. Peripheral nervous system, everything else. This is getting our input and sending out signals to the rest of the body, right? Now, peripheral nervous system breaks down into two other types. You've got your somatic or voluntary and your autonomic. Autonomic's all that stuff we don't have to think about. Cardiac, digestive, reproductive, all that stuff we don't think. Somatic, that's where you're taking notes, or you're playing on your phone, or you get up and stand, or you whatever. That's what you decide to do. That's control like your skeletal muscles and stuff. Now, I'm going to leave that one alone. Coming back over here to autonomic. Everything in checks and balances. Your body has to have checks and balances. So you've got two branches of your autonomic nervous system. You've got one that starts stuff and one that stops stuff. Okay? So your parasympathetic, that's, you might hear it, feed or breathe, rest and digest. All right? And then your sympathetic, fight or flight. Okay, so basically your sympathetic nervous system gets you jacked up, ready to survive. If a bear comes barreling through that door right now, your heart rate's going to elevate very rapidly. Your eyes are going to get a little bit more dilated. You're going to breathe faster, and hopefully you're going to run. Okay? But all these things are happening to prepare you to either run like hell or stay and fight the bear. Okay? To get you through the next few minutes. It slows down your digestion and things like that, because do you need to take a nap when there's a bear coming at you? She's like, yeah. Do you need to digest the crackers you just ate an hour ago if you're about to die in the next few minutes? We're going to put all our energy towards surviving, and then we'll go back to worrying about the digestion part. All right, so it jacks everything up for survival. Then, once the threat has moved on, or we're out of neurotransmitters, whichever happens first, then the parasympathetic system kicks back in, and it's like, all right, we're really jacked up. We're like, ding, you know, heart's going, sweating really bad. It's got to bring you back in, otherwise you'll stroke out. Okay, we can't just keep going up, 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 up. So it brings everything back to status quo. It starts the digestion again. It lowers that heart rate, brings it all back in.
So is that kind of like why if something bad happens or you get excited about something, like if you were hungry before, you're not hungry anymore?
Or if you have to pee, you get that excitement, and then you don't have to pee again, but as soon as the excitement passes, you're like, oh crap, I've got to pee bad. That's why. It numbs those, because it's like, dude, you don't need to pee if you're about to die. And your body can't always tell the difference between roller coaster good excitement, bear it in your face bad excitement. So it reacts pretty much the same. Roller coasters are fun. They're terrifying, but they're fun. You get that adrenaline rush. No? It's kind of addictive. All right, so that's all the stuff that I just told you. Okay, now your brain. You got different areas of your brain that are responsible for different parts. All right, we're going to hit on all those different parts when we get to the neuro section. So we're just going to keep on rolling if that's all right with y'all. All right, but it's there and it does its thing. It floats in CSF, surrounded by meninges. Your layers of the meninges, your pia, your dura, and your arachnoid. Your dura is their durable outer layer. All right, your pia, which one is that one?
That is the one that is like right.
Kind of your
under-
middle layer.
Yeah.
All right, and your arachnoid, spiderwebby looking inner layer, right? There's those things. Cerebrium, thalamus, hypothalamus, brainstem, they all do stuff. We'll talk in depth about the stuff they do when we get to the neuro. All right. Brainstem, though, super important. That's your base person. Without that, you don't breathe. You don't do much of anything. All right. Cranial nerves. I'm not going to ask you to know cranial nerves because, quite frankly, I can't list them all off with 100% accuracy every time. But just know that they exist. What's special about them is they're not coming off of the spinal cord like all the rest of the nerves in the body. They're coming out of the cranium, hence cranial nerves. Reticular activating system's pretty cool. It's in the back side of the brain, and that controls your sleep-wake cycle and some of your vision. That's why if you get a conk in the back of the head, you're more likely to be knocked out, have a temporary loss of consciousness, or see stars in your head, see stars, dark, blurry vision, something like that. All right, spinal cord, 2 different tracks, okay? They're going to the brain and away from the brain. So the one away from the brain obviously is taking impulses from the brain. The one coming to the brain is sending in signals that it's perceiving from the environment, hot, cold, danger, pain, whatever, pleasure, whatever it is. All right. Spinal cord injuries, of course, if it severs the spinal cord, then you don't have that communication route. You can't, if you take out part of the bridge on the interstate, you're not going to get to the other side. Simple as that. All right, your sensory nerves, your afferents, those are traveling towards the cord, which makes sense because sensory input from the outside world. Your efferent is your motor, and that's traveling away from the cord, sending the impulses out. Brain is a control center along with the brain. All of these, you've got endocrine and exocrine glands, and they all make chemicals and excrete chemicals to make other things in the body happen. That's all it does. Sounds like a big deal, right? Just makes things happen. All right, we will talk in depth about all of the different ones, but we're just going to kind of skim on through them because this is another chapter later on. All right, you've got ductless glands, you've got duct glands, you've got the pituitary. Where's that one located?
In the brain.
In the brains. Hypothalamus, it controls what the pituitary does. Pancreas, we already know what that one does. Adrenals, they sit on top of the kidneys. Those are going to control your epinephrine release and making of the epinephrine and release of that. All right, good? All right, GI tract, short, sweet, to the point. Your GI tract, one long tube from start to finish. Got some twists and turns, got some accessory organs, but it's one long tube. All right, starts at the top, works its way down. If all is working properly. Peristalsis is your primary method of movement here. All right, smooth muscle controls it, moves it on down. Fun fact, if you have like paralysis or something, I didn't know it existed until I had a patient one time who had one. And I was like, what is that? Because I'm curious. And they actually make abdominal pacemakers. And he had been shot before and was paralyzed from the waist down. Well, part of his paralysis involved his GI tract. So instead of doing an ileostomy on him, it'd be somewhere. Anyways, an ostomy on him, they actually implanted an abdominal pacemaker, which very similar to pacemakers of the heart, and it created and sent that electrical signal, which caused the peristalsis to occur in the GI tract and moved it on along. Which I don't know, like when they can use it versus when they can't. I just thought it was really cool that it even existed. I didn't know that was even there. Don't be afraid if your patients have something cool, funky, or otherwise interesting. Ask them. All right, because they're usually going to know all the information to tell you about it. You learn new stuff. Anywho. All right. Mouth, pharynx, esophagus, stomach, small intestine, large. What happens in the mouth? You chew most of the time, unless you're my dogs, and they just hoover. Esophagus. What's happening there?
That's where it's going down.
It's going down to the stomach. What happens there?
Getting all acidic and stuff.
It's getting all acidic and stuff. All right, starting to break it down a little bit, kind of a slurry. All right, then it goes off into the small intestines. What's the main thing we're looking at happening in the small intestines?
Your digestion.
What type of digestion?
Chemical
So we're absorbing our minerals, our vitamins, and all the other things that we're getting from the food that we're taking in. What happens mostly in the large intestine?
Water absorption.
Water absorption, because right now we've got a slurry moving through the upper GI, right? Or not upper GI, but the small intestines. If we didn't have some way to absorb the extra water, we'd have nothing but rampant diarrhea. Never trust a fart, be bad, okay? So, the large intestines,
What did you just say?
make sure you're awake.
Oh.
So we'd have rampant diarrhea and you'd never trust a fart.
Yeah.
So as it's moving through the large intestine, you know, it's all squiggly through the smalls. As it comes up, it's going moving through kind of slow, and it's taking in extra water. All right, now, when your fecal matter moves through too quickly, you get diarrhea. All right, a little bit loose, a little bit watery, a lot smelly. All right, if it's staying too slow, if it's not moving along fast enough, you get constipation, big hard turds that hurt really bad. Y'all know what I'm talking about. Don't look at me like you're dumb. You've had them. Everybody has at some point in your time. All right. And then your rectum, which is like your exit point, and then the anus, which is literally the exit point. It's a sphincter. All right. Just like everything else, there's sphincters that go in between the different sections. It's mostly under voluntary control. Okay. So you can kind of and hold it in. Your body, though, doesn't like to be harmed, and so if you allow it to too long, it will override you. Go. All right? When you're looking at rupturing your colon or pooping yourself, your body's going to opt for pooping yourself. Gonna happen. All right? Your esophagus, stomach, your stuffs. Your accessory glands, your salivary glands, where are those located? Inside's usually kind of along here underneath the tongue. You smell something good, they start pumping out. They're like, "Oh, I'm ready to eat it because it smells good." Make you drool a little bit. Liver, we know that's helping break down the stuff. All right, the gallbladder, it's holding the bile, which is going to help absorb the fat. Anybody have their gallbladder removed? No? Well, if you ever do, don't eat fatty foods. Okay? The bile helps bind to the fat and absorb it. All right. If it doesn't, fat's very slippery, and it moves through the GI tract very quickly. It slides all the way through, so you're going to get a little bit more diarrhea if you eat a lot of fatty foods fast. Had a partner one time. She had her gallbladder removed. Man, she told me she had to go. We went. Go brown all the way. Getting her to the bathroom. Serious business. All right. Peritoneum, that's the lining. All right. The visceral lines the organs themselves. The parietal lines the cavity. You've got your mesentery that kind of basically holds it all together up in there, so it's not just free floating and bouncing around. It kind of holds it in place there. All right, there's a picture in case you didn't know. There's some stuff. Your urinary. All right, you got your bladder, you got your kidneys, you got your ureters. All right, so this is where your urine's produced, drains down through the ureters, collects in the bladder until the stretch receptors are activated, and they say go pee. And then you go pee. Once again, sphincter, normally under voluntary control, but will go involuntary if you don't listen to it. All right. Kidneys maintain your fluid balance. They help signal when to release certain endocrine type glands, your erythropoietin to make red blood cells, things like that. We talked about the ureters, they drain down in there. The nephrons are the actual kidney cells that are going to do the actual filtering of the blood, and we will talk more about them in depth when we get to that chapter. But this is the general kind of cross section. You've got your renal pyramids there. That's where most of the filtration stuff is happening out here, and then it collects, drains down into the renal pelvis, and then straight down into the ureters. All right. Reproductive, male side. Of course, here's your bladder. Wait, where's
Y'all on the good. It's in the book.
All right, so you've got your bladder. Up underneath your bladder, you've got your prostate. Your prostate is where semen it's like kind of like a routing chute. So either semen's coming through or urine's coming through, but usually not both at the same time. They've got a much longer urethra, which means they're less likely to have bladder infections. They're less likely to have UTIs because the bacteria has a lot longer track most of the time to get up in there. Okay? And then you've got your testes. We know those are outside of the body because of temperature, right? And you've got your epididymis, Okay, and then you've got your vas deferens, which brings the seminal fluid up and connects down into the prostate. All right. Females, you've got your bladder. On top of that, you've got your uterus. All right. Your cervix is just a muscle, like little muscle. You know those little powdered donuts? It's like one of those without the powder. Right, closed up little muscle, round muscle, and that blocks off the entrance to the uterus. And then below that, you've got the vagina, and then you've got your external, and there's some other things we'll discuss in there, but that's basically it. You've got your fallopian tubes that kind of hang out where your ovaries, they sit kind of like this. So when the egg develops, ovary develops in a follicle and releases an egg, it kind of, you ever seen Alien?
Mm-hmm.
You know how the alien bursts out of the chest? That's kind of what happens with the follicle and the egg. So if they're a little cranky, y'all, give them room. Egg pops out of the follicle. The fallopian tubes are like right there, the little fingers, sucking it up. Hopefully, if all goes well, it goes into the fallopian tube and then is either fertilized or not fertilized and dealt with appropriately. But when it doesn't go up in the fallopian tube, that's where you start getting some of your other types of ectopic pregnancies and stuff like that. But anyways, that's what it does. Cross section looking straight on, it looks like a bull, like the uterus, kind of like a little bicycle seat. You got your fallopian tubes and your ovaries.
Looks like Sid from SE.
I see it. Never seen that before. That'll be Sid. All right. Your testes and your ovaries, they've got your reproductive DNA. You've got your chromosomes. Males and females both carry a set of 23. You need both of them to become a full set of 46. If you're missing some, you'll have some aspect, usually of birth defects to some degree or another. All right. We'll talk more in depth about this again when we get to the penis and vagina chapters. So, complex structures, functions, systems work together to maintain homeostasis. If anything goes out of whack, it puts us into some version of shock, and it has to be either corrected or we'll die at some point. Sometimes it's slow, sometimes it's fast. All right? You need to know how all these systems work, function, and work together to understand why other things are going on.